Hey guys, Miss Peterson here, and today we're going to be talking all about magnets. Okay, you've seen magnets before. You have magnets on your refrigerator. You might have played with a compass, which is just a small little spinning magnet. Or maybe you go and you buy the fancy neodymium magnets, the strong ones. What is magnetism? We're going to be talking about magnetic fields and magnetic permeability. And really where this mysterious force comes from. Okay, so first off, what causes magnetism? Okay, magnetism in any way, whether it is a magnet like this or an electromagnet, which we'll get into more later this unit, is caused by moving charged particles. Okay, in a permanent magnet, or in most of that, these are the spinning electrons inside the atoms. A quantum property of an electron, okay, is its spin. So each electron then has a magnetic dipole moment. All objects have a magnetic dipole moment, and that's what makes them magnetic if they have a stronger one. Now, a single electron can have a magnetic domain, and then if you have a group of atoms, which we call a domain, okay, and there's a bunch of unpaired electrons that are all spinning the same direction, you get all those domains to line up, and that's what creates a magnet, okay? The magnetic fields will always be loops. We're always going to have a north and south pole when it comes to magnetism, whether we have just a single particle like that spinning electron, two poles of a magnet, loops of wires, or a solenoid, which is a fancy word for many loops together. And as far as the domains, you can kind of picture that here. Okay, if there isn't a magnetic field, you might have random domains, where if you have a ferromagnetic material, okay, what's that? Ferromagnetic material is a material that is magnetic, okay? Basically, when we, in our normal vernacular, say magnetism, we're talking about ferromagnetism, where if you have something in the domain of a larger magnet, okay, the domains will line up and amplify the external field. They'll become their own magnet. These are things like iron and nickel and cobalt and the things you typically think of as magnetic. But some things like a paperclip, okay, paper clips are typically made of aluminum, and we know they can be magnetized. They can be picked up by a magnet, but they normally don't retain that property for very long. They're paramagnetic. Their domains will weakly align, but then if you remove that field, they tend to revert back to being random, where ferromagnetic materials will be highly ordered, and then when the field is removed, they'll partially revert, but not completely. The degree of that is what distinguishes ferromagnetic and diamagnetic materials. Okay, tungsten, like light bulb filament, is another good example of a paramagnetic material. Now, diamagnetism is a little funky. Diamagnetism is a repulsion due to that magnetic field. Okay, so for example, copper is diamagnetic, meaning if you have a strong magnetic field, okay, say it's pointed in that direction, and you have a piece of copper in it, its domains will not line up to match the field. They will line up opposite the field. Okay. Yeah. Okay, cool. Okay, cool. You can even feel this if you get a really strong magnet. Hold on one second. Okay. So here I have a copper plate. Copper is not magnetic, okay? If I put this magnet on it, okay, this is a magnet, okay, it does not stick, okay? It's not sticking, staying here on my finger. But it sticks to other things like this nail, okay, very easily. But if instead that magnet is moving, okay, and I can see it sliding down that magnet, the magnetic field created by this is actually opposing that magnetic field. So it slides a lot slower than it would naturally. Okay, naturally, if I put something on here, let me find something that's a little bit similar to this little magnet. So I got a pencil eraser handy. And if I have something similar in size to the magnet, it'll just roll right down it. But the magnet has that diamagnetic property with the copper, so it's resisting it falling just a little bit. Okay. Now, how do we represent magnetic fields? The same way we represent electric fields, with lines that show the direction. Now, for magnetic fields, they are always going to be loops that point away from north, okay? So north is going to be similar to a positive charge and toward the south end. So the south end is similar to a negative charge, okay? Now, one of the weird things is in magnets, these are always going to be loops, okay? Because it's due to that structure of the electron, if you cut a magnet in half, okay, like right there, you still have two whole magnet halves, okay? So the result of that is that for the magnetic field lines, they're always going to be loops. So inside the magnet, technically the magnetic field is going the reverse direction from south to north, okay, because of that looping nature of it. Okay, cool? Okay, cool. Now, each material also has something called magnetic permeability. That's another property of matter. That is the ability of a material to support the magnetic field. The magnetic permeability of free space, so of a vacuum, which we typically use for air as well. I haven't seen an AP problem which uses a different vacuum permittivity. Not to say it couldn't happen, but I haven't seen one. So the units for the vector permittivity of free space are mu naught, which is written as 4 pi times 10 to the negative 7 Tesla meters per amp. Okay, so the units of magnetic field strength are the Teslas, okay, where 1 Tesla means that it would apply 1 Newton of force to a 1 Coulomb charge to accelerate it at 1 meter per second, or that was moving at 1 meter per second. Okay, it's a pretty complicated unit. If you look up the Wikipedia definition of the Tesla, it's like really, really long. So don't worry about it too much, but it is the Tesla. Okay. Now, often with magnetic fields, with electric fields, we normally just work in the 2 dimensions of our page. But for magnetic fields, we will often be working in 3 dimensions. So whenever you have like left, down, up, right, for up, okay, we need to be more specific. Up could mean towards the top of the page, or up could mean like up, out of the page. So typically when we have an up arrow, we're going to mean up toward the top of the page and specify that. And down meaning then toward the bottom of page. Okay, where into the page is signified with an X. Sometimes you'll see it with these circles around it. Sometimes you'll see it without it, but it's the same representation. Now that means that the magnetic field is going into the page. So you have to picture it 3-dimensionally. If you're thinking of it in terms of the coordinate system, Y and X are in the plane of the page, and then Z coming out of the page. Positive would be here, and negative Z would be here, that going into the page. Okay? And we will use those conventions a lot. One of the easiest ways to remember it is to think of an arrow. Okay? If you think of an arrow, if it's coming at you, coming out of the page toward your face, so like look down at your computer screen, it's coming out of the page toward you, that is the tip of the arrow that you see. Where if it's going into the page, then you see the little feathers at the back, okay? Going into the page, away from you. Okay, cool. Okay, cool. So let's talk about magnetic fields and how we measure them. So the first way that we've been using magnetic fields since ancient times has been with a compass, which is just a tiny permanent magnet that is free to rotate. Now, if there is not a larger magnetic field nearby, this magnetic field, this magnet will rotate to line up with Earth's magnetic field. Okay, Earth has a magnetic field at sea level on the equator. That magnetic field has a value of about 3.2 times 10 to the negative 5 Teslas. Okay, so a smaller magnitude. Okay, but if there's not a larger field nearby, that's what your compass lines up with. And that's how we can use them for navigation. Now, if you have a magnet chilling on your refrigerator, holding up your physics test that you got an A on, at the surface of that refrigerator magnet, it's typically on the order of like times 10 to the negative 3 Teslas. And also, these are the values from Wikipedia, very reliable source here. It actually is. When people say things wrong on Wikipedia, they are corrected almost immediately. But on the surface of a refrigerator magnet, it's about 2 orders of magnitude stronger than that of the Earth, which is good because we wouldn't want our magnets to be attracted to the Earth. We want them to be attracted to our fridge. So we need that to be a much stronger field. Now, if you buy a really strong magnet, like a neodymium magnet, there you can get on the order of about 1 to 10 Teslas. Okay. And if you've ever been in an MRI machine, 1.5 to 3 Teslas. But experimentally, they have it up to much higher, like in like 17, 15, 16, 17 Teslas. And that's why you have to take your jewelry off when you go in an MRI machine. But like, it's never going to be attracted to the magnet on your refrigerator unless you put it there. So what does a magnetic field do? Okay. Gravity fields are spaces where they feel the force of gravity, okay, which attracts mass. Electric fields are where they feel the electric force, which interacts with charged particles. What happens in a magnetic field? What is the magnetic force? Okay. Magnetic forces are a little different in that they only exert forces on a moving charged particle. Okay. And that force will be directed perpendicular to the field that is exerting it, which brings us to our right-hand rule, number 1. Okay, so with this right-hand rule, I have the picture there, or I have it here the way that I do it. They do it with the flat hand in this picture. So your thumb is the velocity, your fingers show the direction of the magnetic field, and then your palm is the direction of the force. And I like that because then your palm is the force. It's like, you know, what you hit things with. Or you could do it with your hand like this. And again, your thumb is your velocity because, you know, you go that way. So your thumb is your velocity. Your finger is your magnetic field. So it points in the direction the magnetic field is going. And then your middle finger is for the force. Okay, get it? Because it's your F finger. F, middle finger is your F finger. So you use it for the force. Get it? Get it? That's how you remember it. So that can tell you the direction of the force on a positive particle. Okay, it has to be a positive particle. If the particle is negative, you can either use your left hand or just switch the direction of the force. Okay, and the equation for it is that the magnetic force equals Q, the charge, times the velocity, cross product with the magnetic field strength. Okay, so this is the magnetic force. Okay, Q is the charge. V is the velocity. This is a cross product where you multiply 2 vectors. And B is the magnetic field. In Teslas, velocity, you'll use meters per second, and charge, of course, in coulombs. Now, will you ever actually use the equation in this form? Probably not, unless you've had calculus and you know all about dot products and cross products, and you're like, yep, I can do that. Right underneath the equation on your equation sheet is another form, okay, that says the magnetic force equals QV. They have the vector hats on them. I'll do the vector hats. Sine theta B. Okay, so this here, that angle is the angle between V and B. So if you're using your right hand rule, it's that angle between your finger and your thumb. And that's how we can shortcut that cross product. Also on your equation sheet, it's always in absolute value signs because you should be using your right hand rule to determine the direction of that force. Okay. So the effect of this is, say we have a magnetic field pointed toward the bottom of the page. Okay, so pointed toward the bottom of the page. And we have a proton moving horizontally through it. Oops. So there's our proton, and it is moving in that direction. We use our right hand rule, okay? And you want to be doing this like in the plane of the TV screen or in the plane of your paper, wherever you're writing this down. But your finger is in the direction of the force, okay? The magnetic field is pointed down, okay? So I'm trying to do this like over my page, okay? So the magnetic field is pointed down, so the force is going into the page, okay? The magnetic force is going into the page on this particle. Okay, and that makes sense. This is a 90-degree angle. So theta here would be 90 degrees, and the sine of 90 degrees is 1. Okay, so in this scenario, when the velocity is perfectly perpendicular to the field, you can just use the magnetic force as QVB and have that maximum force. Now, if instead you had that particle moving parallel to the field, okay, if you were trying to do your right-hand rule for this, I'd be like finger down, thumb down, or like opposite direction. It just doesn't work, okay? When the angle is parallel, here it was perpendicular. Okay, when the angle is parallel, or when the velocity is parallel to the field, okay, theta equals 0 or 180 degrees, however you want to think about that, okay, then the magnetic force is going to be 0. Because again, sine of 0 or sine of 180 is 0. And if you ever forget that, it is on your reference sheets. Okay. Okay, cool. Okay, cool. Let's go ahead and do a quick practice problem. We have an electron traveling through a magnetic field. We have its velocity is 5 times 10 to the 6th meters per second. The strength of the magnetic field is 0.4 Teslas. Okay, it's an electron, so its charge Q is going to be negative 1.6 times 10 to the negative 19 coulombs. And then we have the angle, they told us, is 30 degrees. Okay, so they want to know the magnitude and direction of the particle's acceleration. So if it's accelerating, we're going to need the mass in there. So the mass of an electron is 9.11 times 10 to the negative 31 kilograms. Okay. And then we know that acceleration is equal to the net force divided by mass. Okay. It's not talking about any other fields or forces, so we can ignore the gravity effects and all of that. We're just going to do the magnetic force. So we have QV sine theta B over M. And we got Q, we got V, we got our angle, we have B, we have M. So it is just a straightforward plug and chug problem. The acceleration will equal Q. And again, for the magnetic field, remember that it's in absolute values. So we're going to ignore that negative sign for now. We will consider it when we find the charge, the direction of that acceleration. So Q times V times the sine of 30 degrees times B, 0.4 Teslas, okay, divided by the mass, 9.11 times 10 to the negative 31 kilograms. Okay, and we plug that all into our calculator, and we get make sure your calculator is in degrees mode. Divide by 9.11 times 10 to the negative 31. And I got 1.7 times 10 to the 17th. Okay, the acceleration is 1.756. So I'll go 1.76 times 10 to the 17th meters per second squared. And that's it for the basics of magnetism. Next lecture, we'll talk more about the magnetic force and its uses, and then we'll get into electromagnetism. Okay, cool. Okay, cool.